Alright, so in this video, let's take a look at what you need to know about Zener diodes. Again, this is a video basically to give you an idea of how they operate. This is not a video to teach you all about the theory. If you need to know the theory, review any textbook to get a full in-depth theory on it. This is just a what you need to know Zener diodes in a nutshell type of thing. So it's going to be a quick overview of what the Zener diode is, what we talk about when we're dealing with it, and how to actually use it in solving things. So first, let's take a look at the circuit component itself. So the circuit component itself looks something like this. So it's basically a backwards diode like that. And what you have is you have a voltage here, Vz, and you have a current here, Iz. All right, that's simple enough. Now what I want to do is I want to focus on this graph here we call the IV, or the voltage current voltage characteristic. And so basically, if you recall, the diode has a characteristic of something like this here. And this part would go linear up like this. And so this part, we have this small sort of region where it acts as a small voltage for any current. Then all of a sudden it turns on and it has this linear region. Now the only way we can actually use this diode or as a circuit model is if we're working in this linear region, and that's the most useful point to us. It's not useful if we actually work here. We want to be working in this this linear region here. And so if we're working in this linear region there, we need to have established some certain things. So basically, when the voltage here is more negative than V minus VZK, which is the knee voltage, this diode will start to turn on. Once it turns on, it's sitting in this region here, which is basically a linear region. And what we do is we extend that linear region to some point. We call it Vz naught. So we're saying if this is a linear approximation, the value of this voltage when the current is 0 is going to be Vz naught. That means right when the thing turns on, it'll have some intrinsic sort of voltage or potential called Vz naught. And basically what I've defined here as minus Vz and minus Iz are basically any given test conditions, like what conditions you're actually operating under in any given circumstances. The thing to note here is that the slope of this thing is current over voltage, which is inverse of resistance. Sometimes this is called the incremental resistance, or sometimes they say dynamic resistance, because this thing will change based on where you are. I mean, in this region it'll be more or less the same, but you'll notice in some places here it might start to differ a little bit. So how do we actually model this thing? So the model, and by circuit model, I mean like this thing it's great, it's a component, but we need a circuit model to actually solve it. What I do is, well, we've seen this before, so let's just translate everything here. So basically what's going to happen here is I'm going to have the following model for the Zener diode. So we had last time, we have plus minus Vz here, we have a current Iz here. Now what we have is this is Vz here, this current is Iz here, this voltage here is going to be Vz naught, and this resistor is Rz. Alright, so now what do we do? If we want to, we can write a KVL for this. So let's write a KVL for this. So then I have Vz is going to equal Vz naught plus Rziz. And so based on this, you can see clearly that this is a fairly good regulator. And that's basically the main use of a Zener diode, is to regulate, because it'll have Vz naught plus some little change based on the current. But since Rz is going to be very small, it doesn't really make much of a difference in the overall scheme. So you might have like a difference of half a volt in the case of some very large current Iz. There are some things to note, and this model is only valid under some certain cases, and these cases are what? This is when Iz is greater than Izk, so that means this current here has to be greater than the knee current, otherwise the device does not turn on and does not operate the way we want it to. And also we need Vz to be greater than Vz naught. Of course, if this potential here is not greater than this potential here, you have no flow of current, and therefore the device does not turn on. And if not, what happens? The device is off as expected. This means this is an open circuit. So I hope you found this video helpful. If you haven't already, hit that subscribe button so you get notifications when we do upload more videos. And other than that, I want to thank you guys for watching, and we'll see you in the next one.